Good morning, good afternoon, or good evening, depending on where you are in the world. Welcome to our next Nano Explorations student seminar. It's my great pleasure today to introduce Justin Hou. He's a student in electrical engineering and computer science at MIT. He'll be sharing his work on hybridized magnons and van der Waals antiferromagnets and circuit quantum electrodynamics. Again, the Nano Explorations seminar is an opportunity for us to continue to connect with you intellectually and form the community and grow the community that we have as part of MIT, as part of MIT.nano. Justin, thank you for taking the time to share your work with us today, and I'll turn it over to you.
Okay, thanks Professor Anthony for a very nice introduction. And thanks very organizer who makes this webinar possible in this difficult time, particularly Sherry's and Amanda who help logistics and advertisement. So today I would like to talk about hybridized magnons in two different systems. And this is the outline of my talk. First, I will introduce what is the magnons and what is mode hybridization and the underlying physics. And the underlying physics is coupled oscillators. And the first part of my work is about magnon-magnon coupling in antiferromagnetic chromium chloride, which is in collaboration with Pablo's group in MIT physics. And the second part is about magnon-photon coupling in a superconducting resonance system. So the first part. So what are the magnons? I think people who are interested in solid-state physics may heard of photons. So photons describe the lattice waves in a crystal. And photons has a dispersion relations like energy and momentum. And you can see that they have different modes. They are characterized by acoustic mode and optical modes. And magnons are very similar to the photons, but they are excitation of the spin waves. So in the magnets, the spin are pointing to different directions and they can oscillate in a coherent manner. And they also characterized by the frequency and wave vector dispersion relation. And depends on the applied field and propagation direction, there are also different kind of magnons. And both photons and magnons are bosons. So they can be described and understood by harmonic oscillators. And in my work here, I will focus on the k=0 mode of the magnon, which is the uniform mode. So now I will introduce what are the physics of coupled oscillators. Imagine we have two oscillators. You can think them as two magnons. And here they are identical. So the resonant frequencies can be described by a 2x2 matrix. And in this case, it is a diagonal eigenvalue problem. And the two modes are decoupled and degenerate. Then if we introduce another spring connecting them, these two oscillators are coupled together. So this 2x2 matrix become off diagonal. And then due to the coupling, the original degenerate modes are no longer degenerate, and they have avoided level crossing. They have an energy splitting, and this is called anti-crossing. So this is what happened in the frequency domain. So what about the time domain? So people might heard of the normal modes. They can be characterized by acoustic mode and optical mode. For example, to excite the acoustic mode, we displace the two pendulum in the same direction, and they will oscillate back and forth, both to right and both to left. For the optical modes, we displace them oppositely, and then you will see this kind of oscillation. And these two modes has a different oscillation frequency. So from this simple video, what we learned is that the dynamics actually depend on how we excite the system and is correlated with the excitation symmetry. Moreover, the normal modes have properties of both original A and B modes. See, they have amplitude in A and B. This means that we can probably use the property of B to control the property of A. For example, we know that photons rarely interact in vacuum, but if we couple photons with nonlinear matter, we get nonlinear optics. So what about non-normal mode excitation? For example, if we displace them asymmetrically, then we see that the oscillation amplitude is transferred back and forth from B to A and then to B. This means that by this coupled dynamics, we can transfer the energy between the two systems. This means that we can do information processing. And the transformation rate is related to the coupling strength, which is, in this case, the spring connecting them. So we have to define what is strong coupling. Strong coupling means that the coupling strength G is larger than the individual decay rate, so that the energy can be transferred back and forth many times before they die out. So these are Magnons and coupled oscillators. So now I will go to the first part of my talk, which is antiferromagnetic resonance and magnon-magnon coupling in chromium chloride. So this work is in close collaboration with Pablo's group, particularly David, who proposed the first idea of this project. So I would like to start with some examples of magnon-magnon coupling. So these are recently a very hot topic. The first example is that people deposit nickel arrays on an ig film. They are both magnetic material. And due to the presence of the nickel, the ig spin wave will have some standing waves. And these standing waves in the ig will couple with the nickel. And you see the frequency and field dispersion have some anti-crossing. The second example is ig and cobalt bilayer. So the presence of cobalt also causes the ig to have standing spin waves in the perpendicular direction. And this standing spin wave also coupled with the cobalt. So you can also see anti-crossing. To summarize, both magnon-magnon coupling are realized in adjacent magnets. So now we ask the question, can we realize magnon-magnon coupling in a single material? This is an interesting question, but this means that we need at least two modes in a single material. And this also means we need at least two sublattices. And this gives us an idea of antiferromagnets, because in antiferromagnets, two sublattices have opposite magnetic moment and cancel the total magnetic moment. However, typical antiferromagnons have very high frequency in terahertz, and they are very hard to detect. This means probably we need a different material class. So recently, there's a very also hot topic. This is a layered magnetic material. So one of the first example is chromium iodine. So chromium iodine is a cleavable magnetic material, and they show ferromagnetic state in monolayer, antiferromagnetic state in bilayer, and ferromagnetic state again in trilayer. So this is the layer-dependent ferromagnetism. And since then, many more 2D magnetic materials are discovered. Here we focus on chromium chloride, which is in the same family of chromium iodine. So in this paper, it is established that chromium chloride is a layered in-plane antiferromagnetic material below 14 Kelvin. So if we draw their spin directions in the layer direction, they alternate, and the interlayer coupling exchange field is about 0.1 Tesla, which is actually very, very small compared to previous studies. This implies we can probably detect low frequency antiferromagnetic resonance. Furthermore, they proposed a phase diagram. So the vertical axis is applied fields, horizontal axis is temperature. So at very low temperature is antiferromagnetic state. Very high temperature is a paramagnetic state. In between, it is a ferromagnetic-like state. So all of this inspire our study. So to study the resonance, we place the chromium chloride sample on top of a coplanar waveguide, and we apply field in two different directions. One is called H perpendicular, which is the field perpendicular to the in-plane RF field. Another is H parallel, which is applied field parallel to the in-plane RF field. Then we perform the microwave transmission measurement by vector network analyzer. So what we see here is that if we fix the frequency at 5 gigahertz and a temperature at 1.5 Kelvin, we see that with H perpendicular, there's only one mode. With H parallel, there are two modes. To make it more clear, we plot the transmission as a function of both field and frequency. What we see here is that with H parallel, one mode is linear dispersive, and another mode starts at a finite frequency with zero field. And with H perpendicular, only the linear dispersive mode is observed. So to understand the resonant modes, we model the chromium chloride using Landau-Lipschitz-Gilbert equation. So in this equation, the left-hand side is the derivative of the magnetization direction. And the right-hand side is the torque acting on the magnet. The first term is just the in-plane applied field. And the second term is the exchange interaction, which make them anti-parallel to each other. And the third term describes the shape and isotropy, which makes them an in-plane antiferromagnet. So to solve the resonant modes, we solve the canted angle phi with a certain applied field H. And then we expand the magnetization direction around the equilibrium position for the resonance equation. And here, there's a very important symmetry, which means that if we rotate the two sublattices 180 degrees with respect to the y-axis and exchange label A and B, then actually the equation is symmetric because the coefficient HE and MS are the same. And this symmetry is important because they lead to decoupled modes, which is optical mode and acoustic mode, very similar to the previous pendulum case. In the optical mode, we say they have even parity because if we look at the small deviation, delta MA and delta MB, they are invariant if we rotate them 180 degrees with respect to the y-axis. In acoustic mode, it is called odd parity because after we do this rotation, they are opposite. And this symmetry have implication on the resonant frequency. In optical mode, the two sublattices feel the mutual exchange interaction. So when the applied field H is 0, there is a finite frequency. However, in acoustic mode, it is linear dispersive. Therefore, we can understand the previous spectrum as optical mode and acoustic mode, and we can extract the parameter MS and HE, which agree quite well with previous study. Furthermore, we notice that at the acoustic mode, there's a slope change at the field that optical mode dies out. And this slope change is because that when the field is larger than 2 times of the exchange field, then both of the sublattices are aligned with the external field and they oscillate together. So this is similar to a normal ferromagnetic resonance. So after we understand H parallel, we can know what happened is H perpendicular. What happens here is traced back to the pendulum case, which is that the optical mode and acoustic mode needs different excitation symmetry. In our experiment, what it means is that optical mode is excited with the R field parallel to the external field, and acoustic mode needs the perpendicular case. So with H parallel, what you see is that the R field has in-plane and out-of-plane components. The out-of-plane component is perpendicular to the H parallel, and in-plane component is parallel. Therefore, in H parallel, both modes are excited. However, in H perpendicular, both in-plane and out-plane R fields are perpendicular to the external field. Therefore, only the acoustic mode is excited. Besides, we study the temperature dependent of the resonant frequency. At low temperature, we still see 2 modes. This is the antiferromagnetic state. In very high temperature, we see a linear dispersive mode, and this is a paramagnetic state. In between, the frequency and field is not purely linear. And this can be traced back to magnetization data. What we see is that magnetization is nonlinear with the external field in a temperature about 14 Kelvin. So this corresponds to a ferromagnet-like state proposed in previous study. Therefore, our resonance study confirmed the phase diagram in previous study. So up to now, what we have is that we have an external field applied purely in plane. And this in plane has a symmetry of the equations. So in principle, if we have an out of plane field, we can break this symmetry and the previous two modes can be coupled. So we cancel the applied field out of plane. What we see is that when the applied field is in plane, two modes cross each other without coupling. When the applied field is 30 degrees out of plane, then the two modes open a very small gap. At even larger angle at 55 degrees, the two modes have a very, very large gap. And actually in the 55-degree case, the coupling gap is very, very large, and the coupling strength is larger than individual decay rates. Therefore, this is strong magnon-magnon coupling. Besides, the coupling strength is a monotonic function as a function of the canted angle. To understand this coupling, we can model the dynamics using previous LLG equations, and the final result can be summarized by an eigenvalue problem of a 2x2 matrix. So the diagonal terms are just the original modes, and the off-diagonal terms are the coupling terms. And if we look at the coupling terms, we see that when the applied field is in plane, then this coupling term is 0, which means two modes are decoupled. And we can fit our experiment using this eigenvalue problem of the 2x2 matrix, and we'll describe the experiment. So this is the summary of my first part. So first point I would like to mention, chromium chloride provide a convenient platform to study antiferromagnetic resonance in gigahertz and low field. For example, most of the studies of antiferromagnetic dynamics require a terahertz source and a high field, like a few Tesla, which requires superconducting magnets. And here, the chromium chloride is a special material class, so the resonance frequency is in microwave, so you can use microwave electronics to study them. Also, the applied field is very small, so it's easily accessible. Second point is that previous studies realized magnon-magnon coupling in adjacent material. And here, we only use a single material. And the last point is also very important. Chromium chloride is van der Waals material. So in the future, we can imagine we can build a magnetic van der Waals heater structure by combining chromium chloride with other magnetic materials. And we can access magnon-magnon coupling in van der Waals heater structure. Now, I would like to go to the second part of my talk, which is strong coupling between microwave photons and nanomagnet magnons. And I would like to start with a brief introduction of light-matter interactions. So a very famous example of light-matter interaction is called cavity quantum electrodynamics. So this field study the quantum information transfer between the atom and a resonant cavity by shooting the atom through the three-dimensional cavity. And they have observed the Rabi oscillations, which is a quantum information transfer between photons and qubits. And this already won Nobel Prize in 2012. And then there's another field called circuit quantum electrodynamics. So circuit QED borrowed the idea from cavity QED. However, instead of three-dimensional cavity, circuit QED used planar coplanar waveguide resonator. And this is a superconducting material. So this can enhance the cavity mole volume and enhance the energy density to enhance the coupling strength. And the superconductor can maintain the high quality factor even with a very small mole volume. Moreover, a superconducting qubit serves as the artificial atom. So the discovery of circuit QED allow us to do on-chip quantum computation. And you might heard of Google last year claimed that achieved quantum supremacy. So both Google and IBM, those big companies, they use circuit QED architecture for realizing quantum information processing. So most of the case of cavity QED and circuit QED, normally they use electric field coupling. However, in a cavity, there's also magnetic field. So what about magnetic coupling? The problem is that the coupling strengths for the electric dipole interaction are normally very large, in tens of kilohertz or hundreds of megahertz. However, for magnetic coupling, a single spin coupling strength is very, very small, only about 10 hertz. So people propose we can probably couple a lot of spins so that the coupling strength is enhanced by the square root of n, where n is the spin number. And this starts the field of magnon-photon coupling. So in the field of magnon-photon coupling, people place a very large piece of magnets and let them interact with the cavity modes. For example, most of the work are done in the figure, in the central figure. This uses a three-dimensional cavity and a large X field. So the dispersion can be viewed in the right figure. Frequency is depend on the frequency and magnetic field. So the cavity mode is field independent. And the magnon mode, which I say ferromagnetic resonant mode, is controllable by the external magnetic field. And at the mode crossing, they open a gap. This is the anti-crossing gap. And this gap is proportional to the coupling strength G. And at this coupling regime, the modes are hybridized. So people call it magnon-photon polariton, which has both properties of magnon and photon. And I've mentioned we want to achieve strong coupling so that the value of G is very important. And if we look at the formula of the G, we see that beside this square root of n enhancement, the single spin coupling strength GS has a factor which is cavity mole volume. So we see that if the cavity mole volume is reduced, we can boost GS. And potentially we are thinking whether we can reduce the cavity mole volume to achieve strong coupling with very small magnets and make everything on chip and scalable with superconducting resonators. In other words, we are thinking whether we can use circuit QED architecture to realize magnon-photon coupling. Then we start our experiment. So this is a 50 nanometer thick coplanar waveguide superconducting resonator, use niobium. So at the end of the superconducting resonator, there's a gap. So this gap serves as the current node of the current. And due to the presence of this node, the modes inside this resonator have different harmonics. So we design the superconducting resonator so that the fundamental mode is at 5 gigahertz. Particularly, the fundamental mode has maximum current at the middle position. Therefore, we deposit a permalloy, which is a magnetic material, at the center of the coplanar waveguide and let it interact with the fundamental mode. And here, the external field direction is perpendicular to the RF field direction so that magnon-photon coupling can be excited. And let's look at the transmission of this experiment. So without the permalloy, we see there's a transmission peak at about 5 gigahertz. This is because when it is on resonance, photons can pass through this resonator, and we have a maximum transmission. And with permalloy, the quality factor is slightly reduced. So we do the experiment and plot the transmission coefficient as a function of frequency and field. What we see is that there's an anti-crossing, as we expected. And from this frequency dispersion, we can extract the coupling strength G at around 64 megahertz, which is not bad. And compared to the decay rates, it is still smaller than the Magnum decay rates. However, we can vary the size of the magnet by changing our lithography. So what we see is that the coupling strength G scales as a square root of n of the number of spin. In particular, at this data point, we realize strong coupling because G is larger than both decay rates of the cavity and Magnum. In this case, we realize the strong coupling with 3 orders of magnitude reduction in spin number compared with previous studies. So this is very nice, and we are thinking, how can we understand this experiment from a theoretical point of view? So we write down the Hamiltonian, and this Hamiltonian consists of 3 parts. The first part is just the simple harmonic oscillator of the cavity mode. The second part is the Magnum mode. And the third part is the interactions, which consist of operator in the resonator and the operator of the Magnum. So the key question is, what is this GS? GS describes the coupling stress. Is GS still related to the cavity mode volume, as I previously mentioned? So our answer is that this is for 3-dimensional cavity. And here we have a planar structure. So if we look at the literature of circuit QED, we will see that the photon modes in the superconducting resonators are described as LC circuits. What we have here is that this inductor L will generate magnetic field coupled with our Magnum. If we use the LC circuit model, what we see is that we have a new formula in this kind of form. So if we look at the formula, the key parameters are BRF and this Z. So BRF is the magnetic field generated per unit inductive current, and is related to the geometry of the coplanar waveguide, which is the width. Also, we have Z, this is impedance of the resonator, which is related to L and C. And to increase the coupling strength GS, what we have to do is that we have to reduce W, the width of the coplanar waveguide. Also, we need to reduce Z, which is the characteristic impedance. And from this formula, we can actually predict the coupling strengths using theory and compare with the experiment. So we do the comparison, and what we see is that in the experiment, the single spin coupling strength is about 18 Hertz. And the theoretical formula gave us 14 Hertz. And this is not bad. And this means that the theory can give us a guideline about how to improve our experiment. So I mentioned that we need to reduce the width, also reduce the impedance. Then we design a different resonator. And in this case, this is a lumped element resonator. So what you see is that in this resonator, there are a lot of wires. And these wires are the interdigitated capacitor, which maximize the capacitance. And in the middle, this is the inductive wire, which is very thin. So with this structure, we can have a very large C and very small L, which reduce the characteristic impedance. So we also do a microwave simulation about this resonator. What we see is that they have 2 modes. The lower frequency mode at around 5.4 gigahertz correspond to the case that a high current density passing through the central inductive wire. and the high frequency, actually the current is very weak. So we use the low frequency mode to couple the magnon with this cavity. And besides, we can compare the resonator, this lumped element resonator with the covalent waveguide resonator. As you can see, the magnetic field is highly concentrated in the case of this new resonator. And actually, the field strength ratio is about 30:1. So this means that we can possibly get a very high coupling strength using this new resonator. So we do the experiment, and what we see is that, again, we see the anti-crossing. However, this time the permalloy size is very, very small. So it's about 40 micron times 2 micron times 10 nanometer thick. But we still get a very large coupling strength, which is about 74.5 megahertz. So previously, I mentioned the scaling of the coupling strength with spin number of the covalent waveguide resonator. And if we do the same study with this new resonator, we see that the slope is very, very steep. If we extract the single spin coupling strength, we see that the lumped element resonator single spin coupling strength is an order of magnitude larger than the covalent waveguide resonator. This means that to achieve strong coupling, 2 orders of magnitude reduction in spin number is sufficient. This in turn means that it's possible to achieve 5 orders of magnitude reduction in spin number compared with previous studies. So here is a short summary. I have introduced cavity QED, which is a light matter interaction with electric coupling. And by making cavity QED on chip, people are now studying quantum information processing and try to commercialize quantum computation. And besides circuit QED, people are interested in combining other quantum systems into this system. This is called hybrid quantum systems. So in our case, we study light matter interaction with magnetic coupling. And previous case used 3D cavity, which is similar to cavity QED. Our work realized the circuit QED version of magnon-photon coupling. Everything is on chip and scalable. That means that you can use lithography to print a lot of these devices on a single chip with a highly controllable manner. Besides, our system is compatible with the circuit QED. This is because we both use superconducting resonators. This means that in the future, we can couple magnon with photon and then with qubit to make a hybrid quantum systems. So we now ask, what's the advantage of the magnon? So this go back to the pendulum case. So what's so special with this new mode? Our answer is that in the field of spintronics, spintronics try to control the dynamics of the magnons using injection of spin current. So we are currently working on this, try to incorporate the spintronic effect into this system. So let me make a clear example of this hybrid quantum system. Actually, people have already studied the coupling between a magnet with a qubit inside a 3-dimensional cavity. And people can use this qubit technology to probe the magnon quantum states. And you can see there are already 2 science papers about this topic. In the field of spintronics, we can provide another degree of freedom. Means that we can control the magnons by the injection of spin current. And this process is on chip and in the nanometer scale. And this is done within our current architecture. So in the future, we are interested in integrating spintronics effects in these hybrid quantum systems. This has 2 advantages. The first is that we can possibly study the spintronic effects on the magnons in the quantum limit by combining with the qubit technology. And the second is that we can possibly use spintronic effects for potential quantum control. So this is the last slide. I would like to give a summary. We have realized a strong magnon-photon coupling with 3 orders of magnitude reduction in spin number n compared with previous studies. Also, our system is on-chip, lithographically scalable, and using metallic ferromagnets on a silicon substrate. So this is industrial compatible, and you can do it with high precision with a lot of them on the same chip. Also, we have a coupling strength formula, and this formula says that we can design the coupling strengths using the resonance geometry, and we have an approach to further improve them. And we are now working on incorporating spintronic effect in this system. And this is because we achieve very high coupling strengths with a very small nanomagnets, which make spintronic effect efficient. And last point is important because our system is compatible with circuit QED. This is a step toward the quantum spintronic hybrid systems. And this is end of my talk. Thanks very much.
There's going to be some flexibility.
Justin, thank you very much. I send both the virtual clap there, let me click, and the real clap. So thank you for the wonderful talk. We have some time for a few questions. So please either chat or raise your hand. A question came in from Vladimir. It was a similar question to what I was going to ask. You mentioned that the process is lithographically scalable.
Yeah.
What do you think are the challenges actually to do that scaling? Do you have any early indication or suggestion of what yield is going to be, or what some of the limitations may be?
Okay, this is a very important question. So the point is that here we use 2 different kind of resonators, and what you see is that in the second case, the resonator is quite complicated. So I believe this depends on lithography procedure. For example, in this resonator structure, the yield is very low if I do it in EML, but the yield can be very high if I do it in TIL. So I believe this is, the yield is okay. So more than 80% of them will work, but I believe this can be improved if we have an industrial procedure. Yeah.
Very good, thank you. Wanted to say there's another question. Another question came in from Andrew. What is limiting the Q of your superconducting resonator? And would your work benefit from increasing the SC resonator Q?
Okay, this is a very, very nice question. So I have to admit that I'm not the expert of the superconducting resonator, but I would say that for example, after we fabricate this superconducting resonator, we actually see some residue of the photoresist at the edge, and we highly suspect this residue will decrease the Q of the resonator. So I believe further improvement of the fabrication process can be helpful to increase the Q. Yeah, and I might learn from you guys. But the importance of the quality factor on the coupling strengths, I believe our quality factor is high enough because it is in the strong coupling regime. But my point is that if we look at the formula of the coupling strengths, actually the quality factor Q doesn't come in. So I believe as long as the coupling is coherent, then the quality factor Q doesn't change the coupling strengths that much.
Very good, thank you. I'll take one more question here. The system needs to operate at very low temperatures, which might limit its practical implementation.
Yeah.
How likely in the future is that the temperature, will it be that the temperature of operation increases?
So I believe this depends on what you want to do with this system. So for example, if I just want to demonstrate, for example, if I just want to study magnon-photon coupling, actually I don't really need a superconducting resonator. For example, we are working on copper resonators. They are not superconducting, but they can work in room temperature. and that's equally fine. But if we want to combine this architecture with, for example, qubit technology, then the qubit technology has the limiting factor because superconducting qubits, they work in dilution fridge, which is milli-Kelvin temperature. So I would say it depends on what kind of applications that you are looking for.
Very good. Thank you, Justin. So again, Justin, thank you. I'll send the real clap here and the virtual one. Thank you for your time and for your wonderful and exciting research. I wanted to let everybody know on the same time, same channel, on Thursday, we'll have our next Nano Explorations talk. And that'll be by Samantha McBride, a recent graduate, recent doctor, Samantha McBride, from mechanical engineering, who'll be sharing her work on nanoscale phenomena during evaporation of saline drops, salt patterns, and crystal ejection. So that'll be on Thursday, same time, same channel. Thank you for joining us and have a good day.
Thank you very much.